right, the trig is in the past, kind of. Not really, it's never going away. But we're moving on to a new topic. Partial fraction decomposition. I didn't capitalize my F. Oh, well, moving on. Life goes on. All right, so can you add fractions? Yeah, of course we can. Right? Of course we can add fractions. Like, what are we doing? There's no integrals? No. So we just give this one an x plus 4. We get the bottom an x plus 4. We take this one, multiply by x minus 2, x minus 2. There's an implied parenthesis around all denominators, numerators. And we can put it together, right? Oops. So we'd have x plus 4 plus 2 times x minus 2 all over that common denominator of x minus 2 times x plus 4. We could clean it up, bring it in, x plus 4 plus 2x minus 4 all over x minus 2 times x plus 4. Hiya, and we just end up with 3x over x minus 2 times x plus 4. And you're like, why are you talking about this? Well, this is the simple direction. This is a simple direction. But what happens if I give you 3x over x minus 2 times x plus 4? And I say, all right, create two fractions out of it. Just create two fractions. Do the opposite process. Now I'm pausing, I'm waiting. Do you know the opposite process? Well, the opposite process is called partial fraction decomposition. Because if we end up with an integral that looks like such, this might be kind of tough to deal with. Actually, this problem's super simple to deal with. You could just do a U sub and be done with it. But not all problems are going to work like this. This would be much simpler just to do with a U sub. But that's not the point. We're not even trying to do an integral yet. So let's write this and let's see how we're going to break this up and put it into two pieces. All right. Well, here's going to be our game. We know that it's going to end up with, I mean, you probably even remember the problem at the beginning. You're like, I know the answer, but could you get there? Well, it's something over x minus 2 and something over x plus 4. And why did I put parentheses on the x minus 2 and not the x plus 4? So what we're going to do is we're just going to call it some A and some B. And this is going to be our first step to doing the problem. Okay. So what we're trying to do is we want to solve for A and B. But it's like, but we only have one equation. How the heck are we going to solve for two variables with one equation? It can be done. We're going to do something called equate coefficients. So this is going to be our first step. Whenever you have the two linear being multiplied together, you break it up. And now we're going to try and solve for A and B. Here's our game. Let's multiply both sides by the denominator. Okay, so we just bring that stuff through. So we're going to end up with 3x is equal to A times x minus 2. You'll get much quicker with these because you're going to see that things will just cancel out. And then we have our B times x minus 2 and x plus 4. So the x minus 2's cancel out, the x plus 4's cancel out, and we are left with 3x is equal to A times x plus 4 plus B times x minus 2. Let's go! We got to solve for A and B. Now the nice thing is we have a choice. We can choose any value of x that we want. It's an equation. It must be true. It's got to be true, so we can choose any value of x, and I think we should be smart about our values of x. Maybe there might be some simple numbers to plug in that might make a variable go away. Like, what would happen if we plugged in x is equal to negative 4? I think we could solve for b. So let's do that. So let's choose x is equal to negative 4, and let's plug that in. So we're going to have 3 times negative 4 is equal to a times negative 4 plus 4. But that's just 0. We're doing that on purpose to make it go away. So, whack, that's 0. So we have negative 12 is equal to, what is that? Negative 4 minus 6, that's negative 6 times b. Divide by negative 6. And then we have that b is equal to 2. Well, cool. We can go back up top. 2. Now we need to solve for a. So let's use that same trick. Let's get rid of all that. Let's just do right below. Now we want to get rid of the b, so what would be a good choice of x? 2. So we're going to plug that in. So we're going to get 3 times 2 is equal to a times 2 plus 4 plus b times 2 minus 2, but that's just 0. It goes away. So we have 6 is equal to 6a. Divide by 6, divide by 6, and a is equal to 1. Hooray! We can go back up to our problem and just plug in 1, and there it is. But I mean, you already knew the result. I mean, we'd already messed with it. So let's go solve our integral now. Notice how I'm breaking it up into 2 pieces. That is totally unnecessary, and don't know why I'm doing that. Plus 2 over x plus 4 dx. Now these are about as simple as they frickin' come. I don't even need to work down below. This is equal to the natural log of the absolute value of x minus 2. Plus 2 times the natural log of the absolute value of x plus 4, all plus c. And there's our solution. This is partial fraction decomposition. There's a few different scenarios in which we're going to need to tackle. This is the simpler of them. Notice the integration is very simple. The integration is extremely simple. It's the algebra trying to get there that is actually the difficult part of it. So PFDs. Hopefully your pre-calculus teacher did this with you. I know I make certain every time I teach pre-calculus, I'm like, dude, taking pre-calculus, you'd probably want the techniques for calculus. Oh, I don't know, but a lot of us didn't get that opportunity, especially during the pandemic. We missed a lot of stuff. So that's not your fault, but now it's up to us to get better with this. Because I can tell you, when I took Calc 2, I had never seen this stuff in my life. I had no clue what the heck was going on. So, all right, I'll see you in a minute.